Hi, this is George Darakis again, and today I would like to change a little bit the topic and solve a problem that a lot of students find it quite challenging. This is from the web work of McGill University here in Montreal, Canada, and this problem has to do with simple harmonic motion. And that's from the physics course 101, which is mainly physics for pre-med students. So what's the problem? The problem is that we have on a planet, the people that they live in this planet, they use, let's say this is the planet here, so they use a hole that passes through the center of the planet in order to send messages to one another. So, and that of course goes towards all directions. But like for the purpose of the problem, let's just choose, this direction here, which is the vertical direction. So this is a hole that the people that they live in this planet, they send messages, and again for the purpose of the problem, this here it's frictionless. So what we know the radius of this planet, let's say r. We know the density of the planet as mass per volume, and what we want to find, what is the speed of the message that drops. So what's the speed when this message is at distance d equal with a r from the center of the planet, and of course this a here has to be less than 1. We can start here. Sorry, let's say that we want to find what's the speed of the message that drops somewhere here. So, and this distance here is d, and of course this is the radius here of the planet. How we'll approach this problem here? Since we're talking about a mass which is inside some bigger mass, what's going on here? It's the two masses, they are attracted due to the gravitational force, and assuming that this, the mass of the planet is much bigger, that means that this here, the force is acting mainly on on the object which transfers the message. And what will be this force here? This force will be equal with g times m, let's say, of the object times m of the planet over the distance, which is d, so over the distance squared. And of course, here we should put a minus to show that always this force here is towards the center of the planet, and actually it's opposite. I mean, we also have this minus here because the force is in the opposite direction of the displacement, which will go from here to here. So that's the force which is exerted on this object here. And I mean, from Newton's second law, this force here, it should be equal with ma, where a is the acceleration that is acting on the object. What we know here, we know, of course, that the density is equal with m over v. This here, it should be mo, okay, which is the mass of the object. So that means that this and this, they can cancel. And now if we take the equation of the density, we know that density is equal with mass over volume. So that means that, let's say we want to find the mass of the planet, but actually here, the part of the planet that is exerting the gravitational force into the object is only this part here. Is this part here. So it's the part that it's in this circle here. We can call this MP. Now, if we solve for MP, we have that MP is equal with D times V, and D times V, of course, this here is a sphere, so the volume of a sphere is equal with 4 pi r. So in this case, the r, it will be this distance here, which we said is D, so D square. Just not to get confused with this D here, let's say we put this x, okay? So x to the third over 3. Okay, so, and now if you go and you substitute this mass, if you go and you substitute this mass here, what we will have from these two equations, what we will have that g, actually minus g times mp. So we said that mp is equal with d times 4 pi x to the third over 3. And of course, don't forget this d here. I mean, let's just not to get confused. I mean, this here is this distance. So let's call it x squared. So over x squared. So that has to be equal with a. And now you see that this cancels with this, with the third. So what we have that a, or d x squared over dt squared is equal with minus g d 4 pi x over 3. So once we reach this point, we have proved that the object, which is transferring the messages from the one person to the other that they live in this planet, so we have proved that this object theory is doing a simple harmonic motion. I mean, because we have that the acceleration is equal with some constant times the displacement. So that's the equation that proves that the object is making a simple harmonic motion. And if you compare this equation with, of course, the equation dx squared over dt squared is equal with minus omega squared x, that means that the omega for this simple harmonic motion, omega squared, it will be equal with this here. So that means that omega squared is equal with g d 4 pi over 3. So that means that omega is equal with the square root of g d 4 pi over 3. And of course the omega is the angular velocity. And what angular velocity is this here? I mean, because we proved that the object here is doing a simple harmonic motion, that means that this omega here, if you remember from the definition of the simple harmonic motion, that means that this omega here corresponds to an object that is moving in the surface of the planet, doing a circular motion with constant angular velocity, which is equal with omega. So this omega should correspond to the angular velocity of the object that is moving around the planet with the constant angular velocity. So now let's erase. So let's do again the planet here to show you something. So, I mean, let's redo this diagram here. So we have that this is the center of the planet, and let's say here is the the message, and let's say that this distance here is x. So we said that the omega that we find is equal to the angular velocity of an object moving around the planet. So let's say that it starts, the object which is moving around starts from this point here with an angular velocity omega. So that means that let's say at some point the object is in this position, and that means that this distance here, let's call it let's call this we'll call this x. Let's call this distance here y. So if you see from this small triangle here, this angle here, it's equal with omega t, because let's say omega t is equal with theta, because of course this object is moving with a constant angular speed. So that means that theta, the angle, should be equal with omega t, where t is the time that it takes for the object to come here, and of course we assume that t is equal with 0 in this point. So that means that if you take now this small triangle here, you have that y, and of course this here is r, you have that y is equal with r cos omega t. Excuse me. And now, of course, if you take the first derivative of this here with respect to time, that will give you that dy over dt, it's equal with, let's write it here, dy over dt is equal with r times the derivative of the cos is negative sine, so we'll put the negative here, sine omega t, and because you have to use the chain rule, that means that you have another omega here. So that means that dy over dt is equal with minus r omega sine omega t, and what we have to calculate? We have to calculate exactly this here, which is the actually this here is the velocity. We have to calculate the speed, so that means that doesn't matter in which direction is the object going. I mean, it doesn't matter if it's going down or up, because we are actually interested only in the speed, which is just the magnitude of the velocity. So that means that we can ignore this minus here. And here, of course, you have r, you have omega. I mean, omega, we said here, it's equal with omega is equal with gd for pi over 3. So we have r, we have omega. Now the only thing is missing to calculate this answer here is the sine omega t. But we can find that from the basic trigonometric identity that sine of an angle, in this case the sine of omega t square plus cos of omega t square is equal with 1. So from this here we can calculate how much is sine omega t, because the cos omega t we can calculate it from this equation here. If you substitute whatever y equal with x, which we know, I mean the x is again the d, okay? So that means that d over r should be equal with a, which if you compare it with this equation here, should be the cos omega t. So that means that you know cos omega t. From this equation here you can find how much is the sine omega t. So that means that you can find this here, which again we said is the velocity of the object, when it's in this position here. It doesn't matter if it goes up, if it's going up or it's going down, because we are only interested in the magnitude, which is the speed. So that's the answer to this problem. Thank you for taking the time to view this video, and I hope you find it useful, and bye for now.